In this video, we're going to talk about inverse functions. Now, you should have already learned about one-to-one functions and onto functions and one-to-one correspondences, as well as the definition, what makes a function. If you recall, there are two requirements for something to be a function. So, these are required. Onto and one-to-one are optional, but these are required. And the first is for all x in X, there must exist a y in our codomain, y, such that f of x equals y. So in other words, every element in our domain has to have a matching element in the codomain. And the second required rule for a function, to be a function, is that for all x in X and y and z in capital Y, if f of x equals y and f of x equals z, then y must equal z. Right? So these are required. And being one-to-one or onto are properties that functions can have, not that they must have. Okay, so now we're going to talk about inverse functions. A function has an inverse if and only if it is a one-to-one correspondence. All right, this is required. So only functions that are one-to-one correspondences have inverses. And if you recall the definition of one-to-one correspondence, that it means it is both one-to-one and onto. Okay, so we typically write the inverse. So if our function is f of x to y, this is going to be our inverse function, f to the negative 1 of x to y. And again, you've probably run into inverse functions in algebra, and this is really an extension of the same idea. And let's define this. So given any element y in big Y, notice this inverse function f to the negative 1 takes y as input instead of x. X becomes the output. All right, so this is the output, and y is the input to our inverse. So f to the negative 1 of y is the unique element x in big X such that f of x equals y. So in other words, f to the negative 1 of y equals x is equivalent to saying that f of x equals y. So if we have a function, let's make it a one-to-one correspondence. There we go. That's a one-to-one correspondence. It's onto because every element of our codomain y has an arrow coming to it, and it's 1-to-1 because every element of x points to a unique element of y. So if this is the case, then our inverse is really just doing these arrows backwards. So if there was a black arrow here, now there's a red arrow. There was a black arrow here, now there's a red arrow. And notice that it goes from y to x. It's just we're doing the arrows now are backwards. So if I go backwards, so this is f to the negative 1, where the original black lines were f. Just plain old f. Okay, so this is how we define. And now let's take a look at why only 1-to-1 correspondences can have inverses. So I'm going to try and take the inverse of a function that is not a 1-to-1 correspondence, and we're going to see what happens. So this function is 1-to-1, but it's not onto because we have this lone element in the codomain. So it's not it's not onto. Now, if we just take each arrow, and I'm going to draw it backwards. So I'm going to look at this first arrow, and I'm going to draw it backwards here, right? And then I'm going to draw backwards, and then backwards, and then backwards. Well, notice this function over here starts at y and goes to x. So y is our domain. But we have an element in our domain with no matching element in the codomain. If we recall, let's go back to this very first page, that violates the notion that for every element of our domain, there exists a matching element in our codomain, right? Which means this isn't true, but this is required for something to be a function. Which means in this example, this is not a function, right? So f to the negative 1 is not a function. So this is a fail. We can't do this. Right? So when we talk about an inverse, that inverse is implicitly, the inverse of a function is a function. But here we found that the inverse of a function that is not onto is not a function, which means we can't do this. So we cannot take the inverse of a function unless that function is a 1-to-1 correspondence. So we've seen that with one direction. Let's take a look. We saw when it wasn't onto. Let's take a look when it's onto but not a 1-to-1 correspondent and not 1-to-1. What's going on here? Okay, so what happens if we try to do this to a function that's onto but not 1-to-1? So here's a function, f, that is onto. It is onto because notice that none of the elements in the codomain are unattached, right? They all have an arrow pointing to them. But it is not one-to-one because each arrow or each element of x does not point to a unique element of y. In other words, we have two arrows coming into this y, so it is not a one-to-one function. So if we were to take the inverse of this and just do backwards the arrows that we have in the function, now again, recall that f to the negative 1 is now from y to z, or excuse me, y to x. So y is the domain, and this is not a function. Once again, if we go back to the beginning here, where we defined function requirements, we said each element of our domain has to have only a single output. That's really what this one right here is saying, is that if we have two outputs, y and z, for the same input, then y must equal z. In other words, we cannot have more than one output per input. But that's exactly what we've got here. We've got for the input, this input, we've got two outputs. So this is not a function. Right? It violates the definition of a function. And again, in algebra, what this is violating is that vertical line test. If you put a number in, you can't get different numbers out, right? We can't have f of 5 equals 3 and f of 5 equals 9. That's not possible in a function. It's not a function if it does that. So this is another situation where it's not going to work to take the inverse of a function that's not a one-to-one correspondence, because the result is not a function. So only one-to-one correspondences have have inverses. And now we're going to see in the next video, why is that important? Why is that useful?